Hello and welcome back to Introduction to Computational Fluid Dynamics. I'm your professor, Steve Miller. Today we're starting a new module on fluid dynamics, its physics, and its equations, and corresponding boundary condition meanings. This is the first class of this part of the series. This way you'll have an understanding of the physical equations of motions and their particular reductions from assumptions so that you can choose the right set of equations for your CFD solver to evaluate for the appropriate problem. It's critical for computational fluid dynamics practitioners to understand the equations they're solving so that they can make these good choices. In the previous class, we finished our grid generation module. We looked at the connectivity of unstructured grids, and in particular, we talked about what an unstructured grid is and why it's important for particular problems, especially problems with complicated geometry. Unfortunately, the numerical algorithms are limited when it comes to unstructured grids. In particular, we looked at the Delaunay-Vroni method, the advancing front method, which are the two main types of method today to create these types of grids. There's also combinations or hybrids of these methods, which create even more advanced grids. There's alternative approaches, which we touched on, like the quadtree and octree meshing. Finally, we also looked at the surface and volume meshing approach for creating these three-dimensional unstructured grids. In this class, we'll talk once again about the critical fluid dynamics basics that you need to know. This is a little bit of a review for those of you who just took aerodynamics or fluid dynamics 1 as an undergraduate student. We'll look at the equations in their integral form and in the form of the Navier-Stokes equations. We'll also look at and explain the Boltzmann equation, which might be an alternative method for computational fluid dynamics and understanding fluid dynamics problems in general. Generally, in this class and most computational fluid dynamics solvers, we'll focus on approaches based on the Navier-Stokes equations. Let us return to some very basic definitions. First, what is a fluid after all? A fluid is any substance that deforms continuously under a shear stress. So if I have any substance and I have a tiniest amount of shear stress that you can imagine, it will deform. And that is the very definition of a fluid. That's a very broad definition because it's hard to imagine any type of substance that's not truly deforming continuously under a shear stress. But fluids consist of three phases of matter: liquids, gases, and plasmas. In this class, we'll focus mainly on liquids and gases, which are two phases, for example. We will not look at plasmas, but however, computational fluid dynamics has been applied to plasmas, and it's often called computational plasma dynamics. This is because the equations of motion that we look at are coupled in with the Maxwell equations to capture the effects of electromagnetics within the fluid. We'll also have to divide our problems and our equations through a particular assumption, which is the assumption of incompressibility. We'll divide flows, even though we can solve the same set of equations, essentially, into compressible and incompressible flows. The first means, in terms of this class at least, is that density varies, that density is a variable. The second is that the density will remain constant. This is a very simple explanation, but mathematically it's much more complicated, and it can be shown that incompressible flows follow certain assumptions of Euclidean geometry. In the most simplistic sense, the density varies as a function of time at a particular spatial location. This will be seen as a compressible flow in terms of the mechanics of the computational solver. We'll also divide our flows into subsonic and supersonic flows. This is where we need to define the Mach number. The Mach number is m equals u over c. That is a local velocity u divided by the local speed of sound c. This ratio creates a non-dimensional number named for Ernst Mach, and we'll call that m through the class. If m is less than 1, it is a subsonic flow. If m is greater than 1, it's a supersonic flow. If m equals 1 or is in the range of 1 for certain types of problems, we'll call that a transonic flow. And finally, if m is very high, that might be considered a hypersonic flow. In the most basic sense, it's in the community that if m is greater than 5, then it is a hypersonic flow. We'll also classify flows as steady and unsteady. A steady flow is one that is time invariant, or that there's a base flow, or if it's a turbulent flow that's steady, that's statistically stationary. These mean that the average quantities and statistical quantities of the flow, like for example turbulent kinetic energy, the fluctuations in the energy of the fluctuations of turbulence, are not changing with time. We'll call these statistically stationary, or we might call them time invariant. We'll use these terms interchangeably, so try and make sure you make a note of them now so that you're not confused later in the class. Viscosity is a measure of the type of resistance to the shear when the fluid is in motion. For example, a very simple form might be shown as tau equals mu, which is the first coefficient of viscosity, times partial u partial y. Here in this figure, there's a moving plate and a stationary plate. The moving plate moves from left to right in this particular case at a speed of u. The bottom plate is stationary. This is called the so-called Couette flow. Now, if the fluid is just initially a stationary point and we start moving the upper plate, a linear velocity gradient will form between the two plates if it remains laminar flow and stable. Here, we might plot the velocity profile as a function of y, where y is the distance from 0 at the stationary plate to y equals perhaps L at the upper plate. It creates this linear range. Now, if we take a fluid element and put it over on the right, we can show that there's an equal and opposite shear stress balancing the fluid in this particular case. And this shear stress goes as tau equals mu of partial u partial y. This is the most simplistic way to introduce viscosity to most undergraduate students. Now, if we look at graphs of the shear stress versus shear strain rate, partial u partial y in this case, versus tau, we can plot these types of graphs. These graphs can be created, of course, by putting different types of fluids between a moving plate and a stationary plate. And you'll see there's a whole range of particular types of fluids in this case. There's plastics, dilatants, and non-Newtonian flows. And if this relationship is linear between, say, tau, the shear stress, and the shear strain rate, then it's called a Newtonian fluid. Nonlinear shear stress strain rate relations are called non-Newtonian. In this class, we're mostly going to be universally focusing on viscosities that are corresponding to Newtonian fluids. Can you think of some non-Newtonian fluids? One might be perhaps honey or ketchup. In the beginning of this class, we briefly talked about different types of flow regimes. We'll have to have an idea of the type of flow that we're trying to model before we can solve it in computational fluid dynamics. In general, we are going to divide our flows into 3 regimes. That's not to be said that there's not even more classifications, but these are the 3 main classifications you're going to run throughout your career. The first is laminar flow, which moves in perhaps infinitely many layers, and you can think of this as perhaps a laminate. You can imagine taking your hands and sliding them across together in a laminate way. The fluid or streamlines and fluid volumes that are being moved and transformed within the flow are not crossing each other. They're just being continuously deformed. This is typically what we call a laminar flow. Of course, there are some assumptions in my statements, but generally you can see laminar flow in your kitchen. When you turn on your faucet, you can watch the water stream. We discussed this type of experiment in your kitchen in the beginning of the class. But if you barely turn on the water, of course, a rod of water comes out and is very clear and it's not moving very much. This is very much like a steady laminar flow, which represents a jet of water. The second type of classification is a transitional flow. This is where the flow itself starts to develop instabilities, and these instabilities grow and decay, and it might transition to turbulence and might transition back to laminar flow at a time-varying rate, and it's generally very much unpredictable. Finally, there's the flow which we see most often in engineering, which is the turbulent flow or fully turbulent flow. This is a flow where the so-called wave number energy spectrum of the velocity fluctuations are generally all non-zero for fully developed flow. This might be seen through many different types of mathematical theories and represents in its understanding one of the last classical problems of physics to solve. We will talk about the modeling and theory of turbulence for a few classes later in the semester. Now in the lower left corner, we have plotted some streamlines of perhaps a laminar flow. In this case, it's this nice simple flow moving from left to right. In the turbulent case, on the lower right of the screen, you'll see some streamlines were going around in curls in every which particular direction. It's almost unpredictable in a deterministic way. In fact, in CFD in general, we are going to be predicting turbulent flows through statistical approaches and not through just simply finding the solutions to the equation by integrating them, which is one particular approach to CFD. However, most industry applications do not use such approaches and they use statistical approaches. You'll see that if you try and compare a time-dependent prediction between an experiment of turbulent flow and your CFD calculation, that they will probably not match, but they will have the same statistics derived from the temporal solutions. This is why we often compare turbulent statistics of flows to experiments and their derived statistics, not one-to-one comparisons of, say, velocity fluctuating with time, which is done extremely rarely. In this class, you're going to have to decide before you run your CFD solver if the flow is laminar, if it's transitional, or if it's turbulent. Often you'll have to make that choice before understanding what the flow might even be. So you'll have to make intelligent decisions based on, say, flow speeds and Reynolds numbers and these types of things. This can really only be gained with experience, and with time, I know that you can do it. The next classification of the flows is really to do mostly with the type of problem and not so much with the equations and motions. And this is, of course, the external versus internal flows classification. It's as simple as saying, is this flow external to, say, a body, like around an aircraft, or is it internal, for example, through the nozzle of a rocket engine? Here we've shown some examples. In the upper left, we have an external flow, which we've shown multiple times in this class. Flow moves from left to right, and the streamline shown, there's a point of separation and a turbulent wake behind it. You can also see that this flow is likely a subsonic flow. It's also a flow that contains multiple regimes. That is, there's a laminar flow in front of the cylinder, there's a transitional flow on the side of the cylinder, and there's a fully turbulent wake behind the cylinder. That's very frustrating because we'll have to have a CFD solver that can capture all of these effects simultaneously. It could also have effects of compressibility, so you may not be able to make the incompressible assumption. Another external flow is shown in the upper right corner and lower left corner for the same airfoil, only at two different speeds. The upper right one shows different flow regimes of laminar flow and turbulent flow and a potential flow in the subsonic regime. In the lower left corner, we see the same type of flow, but with a Mach number of greater than 1. Therefore, the velocity is higher if we hold the speed of sound constant. Nonetheless, if Mach number is greater than 1, it is a supersonic flow, and you see a shock wave forms. In this case, we have different flow regimes of supersonic, transonic, subsonic, and we have laminar flow, transitional flow, a potential flow far away from the body, and turbulence in the boundary layer and wake of the airfoil. You can see that these problems are very challenging for the solvers because they consist in multiple flow regimes. Finally, in the lower right corner, we show one example, of course, the internal flow of, say, a pipe or a couette flow. And these flows are equally complicated to external flows. Here, the flow might enter the pipe, and it's initially a top hat profile. Over time, it becomes a laminar boundary layer profile, like we talked about from Blasius. This will then transition from laminar flow to turbulent flow through instabilities within the boundary layer of the laminar boundary layer, and then transitional boundary layer. It'll then break down into fully turbulent flow and create a turbulent boundary layer. We'll talk about this process later in the class and how to solve these types of problems with computational fluid dynamics. For now, it's important to really understand and keep track of the classifications. Now that we have some different classifications of our flow, let's turn towards the mathematical modeling of the fluid dynamic equations. We need to seek models of the equations in forms of sets of partial differential equations, or integral equation, but we will be more so likely familiar with partial differential equations in this class. And then we can model and hopefully predict the dynamics of these flows with these particular equations. We will refer throughout this class to the field variables. These are nothing more than the unknown variables like densities, velocities, pressure, and temperature, and perhaps more, in the particular volume or surfaces of the fluid if we're in 2D for surfaces and 3D for volumes. Typically, for most problems that are compressible, there'll be 5 that we're mostly concerned with. And these will be density, the velocity components, and an energy term. You can imagine these correspond to the momentum, the conservation of mass, and energy equations. Now, generally, we cannot solve these equations analytically except for very specific flows with very specific boundary conditions. These are particular solutions that we might be able to use today to benchmark our CFD solver to see if we can find the same solution. So, in general, you can say that no analytical general solution of most of these types of equations exists for general problems. For example, an analytical solution for the one-dimensional wave equation was presented earlier in the class. That's a very simple linear partial differential equation with a celebrated and very complicated analytical solution. There is no such analytical solution for these equations we're looking at now, so we're doing the numerical approaches. Now, as our domains, which are computational, are finite and stored in a computer and must be stored everywhere in the domain, we must turn to digital computers to solve the problems. The domains are also finite. Now, domains in nature can be very, very large, for example, the atmosphere, but it's not very likely to put in a rocket or aircraft and model the rest of the aircraft from, say, the United States all the way to the other side of the world to approximately Australia. That would be too large of a problem to also resolve the aircraft in the atmosphere typically. So we must truncate the domain around just the aircraft. That's the region of the problem where we're interested in the solution. We should also set the solution domain so we do not alter the flow due to the truncation of the domain. If we truncate or split our fluid at a particular point in space, we might actually alter and ruin the solution everywhere else through that truncation or poor boundary condition placement. We'll talk a lot about boundary conditions, their selection and placement later in the class. They affect your solution and are critical for high-quality CFD work. Now let's look at the integral form of the continuity equation. This is a very physical law. Here, we write the integral equation for the conservation of mass. You might view this as something like from Reynolds transport theory. It's very much alike, but not exactly the same. You hopefully have derived the integral equations and differential form of the Navier-Stokes equations in your previous class. If you haven't, please look at a book which you can find online, or perhaps you've kept your fluids or aerodynamics book and look at the derivation. We're simply going to review the equations here and talk about the physical meaning. In the lower left, we have the integral form for the continuity equation. We have one particular integral over the so-called surfaces of rho, the density times the velocity vector v, dotted with each particular surface element. That's the inner product of rho v dot dA surface integral. That is balanced by the negative partial time derivative of an integral over the volume, the control volume. Mind you, CS is control surface, CV is control volume here, of the density in the volume itself. So over here, this can be illustrated in this figure. We have one particular arbitrarily drawn control volume with surfaces. The surfaces are labeled with A. There's a particular vector V, then there's a surface element vector dV. There's streamlines going through the fluid. So it's a very straightforward process to analytically integrate this type of particular equation, either term, if the velocity vector and density are well-known continuous functions. This is very simple and straightforward, and these are typically what's done with pen and paper in your previous classes when solving introductory fluids problems. You've probably looked at incompressible flow previously in this class, and you would say, hey, my density is a constant. I would have pulled it out of these integrals, and then I wouldn't have worried about it. The left-hand side, if it's incompressible in study, would just reduce to a mass flow rate term for mass flow rate going in and out of your control volume. The right-hand side would have been set to 0. We're not going to make any of these assumptions in this class. It's too simple for general problems. So now we're trying to solve the equations of a computer for realistic flows. Of course, the most important set of the equations in the Navier-Stokes equations is the momentum equation. This is the course based on Newtonian mechanics of the second law. You should know that there's also formulation for these equations in relativity. So people do study relativistic fluid mechanics. Here, we're only going to focus on the Newtonian form, and the entire industry, especially in aerospace, is almost entirely focused on the Newtonian form. It works well. Now, we'll have a conservation law for momentum. Here, there's some force F sub s, which is the total surface force on the surface of our control volume. Please refer to this control volume continually through this discussion. There might also be a body force on the fluid. This could be something like gravity. So this is the volume integral of the vector of gravity, perhaps, or maybe it's a magnetic force. But we would also have to additional Maxwell equations for that. These two terms, of course, are balanced by the right-hand side, which is the partial derivative of the momentum in the volume, the specific volume, added to the momentum flux, which is this last term, which is V rho V dot dA. Now, if we take this volumetric equation and make a steady assumption, we can get rid of course, the partial derivative. And if it does not have any body forces, we can get rid of the body force term, which is the second term. So then we would have the forces on the surface, which would be the pressure and shear terms, which would involve the internal stress of the fluid pressure, and the shear stresses, which we previously talked about, would be balanced by the momentum flux term. Now, that's fine, but of course, the viscosity in fluid is very important, especially in turbulence. So this form of the equation, we would not be able to hope to truly resolve turbulent flow, which is mainly what is happening in fluid dynamics and aerospace engineering. So this would be a horrible assumption to exclude viscosity in many cases, especially if we care about turbulence. We can also write this conservation law for momentum in the term for angular momentum by taking a moment. And in this case, we have a new vector r from some point in space to every fluid volume, and we get a momentum equation that conserves angular momentum instead of the traditional momentum. Finally, there's the energy equation, which is of course based on the first law of thermodynamics. I've represented the same figure previously in the upper right-hand side. Here, we rewrite the first law of thermodynamics. Q minus W equals delta E. This is a simplistic form, but it illustrates our problem. Here, we'll say Q is the heat added to the system, minus the work from the system will be balanced by the change of energy in the system. Recall the energy is some internal energy associated with the molecular and atomic behavior, and that is added to the kinetic energy, which would be 1/2 times some mass, or part of the mass of the fluid, times the velocity squared, times some potential energy of mass times gravity times some height. Now, for very dense fluids, we would always want to include the body force term in the momentum equation and also include this term within the energy equation. Typically for high-speed aerodynamics with gases and plasmas, we would drop these types of terms. They don't affect the flow too much. They might also be important for instabilities within the flow. As I said, 1/2 mv squared is the kinetic energy, and mgz is the potential equation. We can rewrite this in an integral form, which I hope you've done previously in your previous class, and we'll find the derivative of the heat transfer added to the system in time minus the derivative of the work done to the system in time will be balanced by the change of energy term on the right-hand side. This is very much like a Reynolds transport theory type equation again, and it can be derived that way. Here we use little e to denote the internal energy plus the kinetic energy plus the potential energy. You can see it's a little bit different than the so-called previous term. Essentially, it's a per unit mass term. So this is how we remove the density from E, capital E that is. In this case, the second law of thermodynamics states that the change of entropy minus the heat transferred to the system divided by the temperature is equal or greater to 0. This is a simplified form of the entropy equation, but it's useful for this particular class. If you really want to understand entropy, you'll have to understand quantum mechanics, and you'll see these types of entropy formulations and the reduction to the particular equation shown here. You can imagine if I have a flow field and I can calculate entropy from the pressure and temperature, and I can find Q in the flow field over some particular time, that this particular inequality must be greater than 0. If it's not, then there's some error or problem with the simulation. Now we can write an integral form for the conservation law for entropy in the form shown on the page. This will be partial T of the control volume of the density times the entropy plus the control volume, the fluxes per entropy per unit mass, which is specific entropy, which will be balanced minus the flux of the heat transfer over some time. This must all, of course, be greater than 0. Now, we've looked at the volumetric forms. These volumetric forms of the equations might be directly solved from a finite volume solver. Of course, we'd have to have the addition of viscosity in the particular term in the momentum equation, which I pointed out a few slides ago. In finite element and finite difference solvers, we will be solving the differential form of the equations. And these are the types of equations which are, at the undergraduate level, derived from the integral form. Generally in graduate school and in research in math and physics and engineering, these equations are derived first and then integral forms are found. The simple explanation, and this is confusion for many students entering the field, is that it's done through the integral form first because it makes more physical sense to most students. On the other hand, there'll be a few students who the integral form makes more sense. It's simply your preference. You'll just have to get used to working with the integral form, and I realize that many students just don't particularly like this form, and that's okay. Now, we can rewrite our equations one more time. Let's look first at the differential form of continuity, which we've written in multiple forms. In the most general form for this class, we've written partial rho partial t plus partial xi rho ui equals 0. Recall index notation. These sub i's are sum. They are the dummy index. In 3 dimensions, the full equation would read partial rho partial t plus partial rho u partial x plus partial rho v partial y plus partial rho w partial z equal to 0. You sum the second term from 1 to 3, but there's a repeated index. Please go back and review Einstein or index notation if you don't recall this. Now, we can also write the equation in the more familiar terms of vector notation. It's much more common to see the index notation in fluid dynamics than it is perhaps the vector notation. This would read partial rho partial t plus nabla with the inner product, or dot product if you will, with the density times the velocity vector equals 0. They are equivalent equations exactly. Compare the two. We can also expand them out and write them in Cartesian forms. I read this equation verbally from the first equation. You can also expand the second equation from vector notation to Cartesian notation, if you so desire. If we make the incompressible assumption, we will let the density be a constant. If you look at the third equation, you can imagine now the density is a constant within the fluid volume, and we can pull it out from the partial derivatives. So for example, we'll have rho partial u partial x instead of partial rho u partial x. Then also, the partial rho partial t term would go to 0 because density is a constant. It's not changing in space or time. So we can divide density throughout the whole equation once we set partial rho partial t to 0, and we'll have, of course, partial u partial x plus partial v partial y and partial w partial z equals to 0. We can also make a steady assumption which is separate from the incompressible assumption. We might say, hey, this first particular equation, or second particular equation, or third, is in fact steady. That means all the partial derivative terms will be set to 0. The flow is time invariant. It's steady or statistically stationary. So we would arrive at the equation at the bottom of the page. We would have nabla dot rho v equals to 0. This is essentially the divergence of the momentum per unit volume, which will be to 0. You can also make an incompressible assumption that is steady. This would then mean that we take rho outside this operator and divide it by both sides, and we would just simply have the divergence of velocity is 0. This is the so-called D'Alembert condition itself if it's in the incompressible form. The D'Alembert condition, that is essentially the conservation of mass. Let's now turn our attention to conservation of momentum. What we haven't done is talk about the shear stress tensor. Let's do that now. Remember, the shear stress tensor has a particular notation. Here we have our arbitrary fluid volume or fluid element. Traditionally, this is called the fluid parcel, especially so in the 17 and 1800s when these equations were being talked about, especially with stress tensors. So here we have 3 axes, the x, y, and z axis. And our fluid parcel, or volume in this case, I'll use these terms interchangeably, is located at the origin. And it has some small differential elements. On each of the faces, we might model the particular forces. This little value, sigma 1, 1, would be represented in this tensor. This is not a matrix. It is in fact a tensor, and that is because it has certain properties when rotated. Matrices do not have these particular properties. So remember to reference this as the stress tensor and not the stress matrix. Anyway, on the x face surface, we'll have a particular stress, sigma 1, 1, and then the transverse stresses will be sigma 1, 2 in the y-x direction, and sigma 1, 3 in the z-x direction. We'll have corresponding stresses on each side. We can write this as the tensor on the right-hand side. You'll notice the diagonal terms of the stress tensor are the normal stresses. The ones on the off-diagonal terms are, of course, the off-diagonal or shear stresses. Let's look at one row in particular. The first row represents all the x components of the stress, sigma 1, 1, sigma 1, 2, sigma 1, 3. The first index, or subscript in this case, 1 means x, 2 means y, and 3 means z. If you look at the third row, you'll find in the first element the zx shear stress. The third element will be the normal stress on the z face. So you can see the diagonal of the stress tensor, in fact, contains the normal stresses. The off-diagonal terms contain the shear stresses. This is critical to remember. And you'll note many fluids have a symmetric stress tensor. That means that sigma 2, 1 is equal to sigma 1, 2. This will be critical later in the class when it comes to turbulence modeling and has profound implications in the mathematics. Let's now look at the differential form of the momentum equation and expand it out in ways so we can see all the terms. We'll only do this once, and we'll typically write it in index notation or vector notation interchangeably. First, the Einstein notation or index form will be here, where we write rho of the material derivative or the total derivative. The material or total derivative is written with a capital D. These are written down in vector form in the bottom of the page for your reference. It is written as partial v partial t plus v inner product with nabla operating on v, the velocity vectors. If we expand that out, we'll have partial v partial t plus nabla v squared over 2, the magnitude of the velocity, minus v cross nabla cross v. This is written in two particular forms for your convenience, so you can see different forms. Now, in this right-hand side, we also have a particular density times partial ui partial t plus uj partial ui partial x. This is simply expanding the material derivative into the index notation. Balancing the left-hand side of these equations, remember these two terms are the same, it's just the material derivative is being expanded out into the index notation. And you might see this is a very interesting term. The I is alone. The j's are the dummy indices. Recall the momentum is a vector quantity. If we set I, we would get the Cartesian form of the x direction of momentum. I equals 2 would be the y direction, and I equals 3 the z direction. We would sum for a constant I, 1, 2, or 3 for each equation, j from 1 to 3. You can see this down here in the Cartesian form in a minute. Balancing this equation on the right-hand side is the partial derivative with x sub j of the shear stress tensor, which we just shown on the previous page. We'll show the full form of the shear stress tensor in a second. This would be added and balanced by so-called body forces. These might be 0 for air and plasma. Let's expand the compact Einstein form into the Cartesian form. You'll have 3 equations, each for the particular x, y, and z direction. Let's just look at the x equation, and you can look at the y and z equations on your own. On the left-hand side, once again, we'll have simply the density times the material derivative of u with respect to time. That will be equal to, of course, the density times expanding out the material derivative term, which is partial u partial t plus u partial x plus v partial u partial y plus w partial u partial z. This will be balanced by the right-hand side terms, which contains the effect of the internal shear stress from pressure and the shear stresses of viscosity, for instance. We'll have partial sigma 1, 1 partial x plus partial sigma 1, 2 partial y plus partial sigma 1, 3 partial z plus the body forces. Look at how those are related to the fluid partial element itself and, of course, the shear stress tensor. Anyway, what we haven't talked about is the actual shear stress tensor form in itself. The derivation of this tensor is very complicated, and it was first done successfully by none other than Navier, which we discussed in a previous class. It was then formalized and put in this particular form, Cartesian that is, by the great mathematician Cauchy, who's also French, just like Navier. Years later, Stokes used these problems and found particular analytical solutions that correspond to slowly moving spheres on a pendulum. This is why the equations are named after Navier and Stokes. Let's talk about the form of the shear stress tensor originally proposed and modified by Navier and then Cauchy. On the right-hand side, you'll see that we have pressure. Many students ask me, what is pressure? it is formally defined as the internal stress of the fluid. We'll say that the negative pressure times the Kronecker delta function of Ij, which we'll define in a minute, is added to the first coefficient of viscosity mu plus partial ui partial xj plus partial uj partial xi minus 2/3 times the Kronecker delta function of partial uk partial xk plus zeta, which is the second coefficient of viscosity. Okay, now it just so happens there's a relation proposed by Stokes called the Stokes hypothesis that relates the first coefficient of viscosity with the second. Is that confusing? Perhaps, but you'll see these equations and the Stokes postulate shown later in the class. This is the full form without such an assumption, which is still under some debate in the research community. Anyway, the second coefficient of viscosity will be multiplied by a Kronecker delta function of partial uk partial uk. Now, let's talk about the Kronecker delta function. The Kronecker delta function will be 1 when I equals j and 0 when I is not equal to j. Now this term is inserted into, of course, the index form of Einstein notation or the Cartesian form. If we put it up here in this term, then you can imagine we are setting I equals to 1 and letting j sum the 1 to 3. So in the I equation, or the x equation in Cartesian form, only the term partial sigma 1, 1 for I equals 1 and j equals 1 would be having a term of a pressure, partial negative partial p partial x. The other terms, say negative partial p partial y and negative partial p partial z, would be 0 because of the Kronecker delta function here. Notice the Kronecker delta function does not appear in the second term and appears in the third. So you can imagine that the diagonal terms of the stress tensor in the form of the Navier-Stokes equation, momentum equation, would be much more complicated than the off-diagonal terms. Recall the D'Alembert condition. Do you remember what it is? It is the incompressible condition, essentially. Here, that means that, say, partial u partial x plus partial v partial y plus partial z partial w would be to 0. Now you'll see we have k summed in this term. We would sum k from 1 to 3. So this term would correspond to the D'Alembert condition. So would the last term in our system of equations. So what happens in an incompressible flow that's steady or unsteady? These two terms, the second coefficient of viscosity term and the second term, would both be set to 0. This would mean that only the pressure gradient term and the first coefficient of viscosity term without the negative 2/3 part would be set to 0 in the particular equations of motion. This is quite wonderful, and for incompressible flows greatly simplifies the viscous terms that would need to be calculated. In fact, these types of terms might be sometimes called dilatation terms in the equations of motion themselves, because the fluid parcels are growing in volume and shrinking in volume. It's not so much to do with density, it has to do with the dilatation of the parcel. This is what I was referring to when talking about the simplification of the discussion of the density terms in the Navier-Stokes equations. The energy equation for specific energy in differential form is written here in index or Einstein notation. A lot of these terms should now look very familiar to you, but we have a few extra terms themselves. Here we define specific energy as the kinetic energy plus internal specific energy plus some value psi. Now in the energy equation itself, we might make some simplifying assumptions. For example, with Fourier's law. We might say that phi is the dissipation function, is the rate at which the shear stress does irreversible work on the fluid. We might also approximate the heat transfer term as negative k, which is a heat conduction or thermal conduction coefficient of the fluid, with the Laplacian of the static temperature in the fluid. I've divided the other terms of the energy equation here. Take a few minutes and examine them. The form of the energy equation is more varied than the momentum equation and conservation mass equation in CFD theory and practice. There are many different types of the energy equation. Instead of the specific energy, we might have an energy equation written for pressure or temperature or entropy instead of the energy equation. And depending on the application, use of different energy equations might give some advantage or particular disadvantage. The specific form of the energy equation is probably one of the more general forms of the first law of thermodynamics. Now, for example, down here I've written some particular forms as examples. One is for enthalpy, H, which is being operated on by the material derivative, and that would also be equal to a form of the equation on the right-hand side involving static pressure. Look how different this form is for the enthalpy relative to the specific internal energy. We can also write an even simpler form using more assumptions of the fluid to find an equation for temperature. So what you can see we're missing from all this is a gas law. We have field variables, but we need to close them with additional equation, which is a gas law. That might be the perfect gas law in the most simple case, like P equals rho RT. Let's finally look at the entropy equation example. This is not typically used in fluid mechanics. Here we will say that theta is the entropy rate production per unit volume. Then we can write an inequality like this. Notice this is not an inequality like the second law of thermodynamics. S remains, of course, the entropy. We would also apply Fourier's law, just like we did in the middle equation on slide 16, to obtain a definition of the entropy rate per unit volume. This is also a volumetric equation which can be used in fluid dynamics for CFD, however, is used for generally very specific situations. However, it should still hold, even if we're not solving it in the CFD solver itself. Let's now summarize the Navier-Stokes equations. Here we have the continuity, the momentum, and energy equations, where E naught is the total energy per unit mass. E naught equals E plus, which is the internal energy, plus the kinetic energy. So E naught is the total energy of the fluid. Remember, U is velocity, rho is density, and T is temperature, P is pressure. Q is that heat transfer rate found from Fourier's law. These other terms are placed in the equations. PR will be Prandtl number, which is a non-dimensional quantity. Tau ij is, of course, the shear stress term. And in this form, you'll see I don't have a second coefficient of viscosity. I've used Stokes' hypothesis. This is probably the most common form of the differential equations of motion, the Navier-Stokes equations with an energy equation that are compressible and unsteady that are used in CFD. We would typically go to these equations to create turbulence models themselves, which would be evaluated by CFD later in the class. In the last part of this class, I would like to talk about an alternative form of equations for fluid motion beyond the Navier-Stokes equations. This is more of an emergent field in computational fluid dynamics, and we'll look at these slides very briefly, but we won't explain them in great depth. You're welcome to read more about this on your own if you wish. Just know that with the Boltzmann equation, named after Ludwig Boltzmann, who created the equation, or found it, depending on your opinion if mathematics is created or found, he has found this set of equations where if we take moments of it, we might be able to recover the Navier-Stokes equations even, or solve them directly. Professor Boltzmann says that to describe a state of a gas statistically, we'll define a distribution function f. This is like a probability density function, such that f dx dv is the average number of particles contained in a volume element. So you can see this is a statistical approach, essentially. And x and a space velocity element dv about v in time t. Now, the so-called properties of the gas are now defined about this so-called distribution function. N at any point x in time t in the field will be the whole integral over the whole domain, three-dimensional domain, of f dv. The density will then be defined as the mass of each particular particle times n. The velocity would be nothing more than 1 over n times the integral of f, which will be the average of v. Here, we'll say n is the so-called number density of the particles, and m is the mass of a single particular particle. You can modify this approach for, say, gases like air, where each particular particle has a different mass. Now, the actual velocity would be nothing but the average plus a random quantity, which would be w. Now, if there's no collisions, a Russian mathematician named Vlasov took Boltzmann's equation and put it in this form. He proposed this differential form, which is a modification of Boltzmann's differential form, because there's no particular collisions, it's a simplification. You'll have this differential equation for the variation in distributions. Here, a is an acceleration, and F will be a force acting on the particles. Recall m is the mass. Now, to account for these collisions, we must have a term that accounts for particles that end up in other particular volumes. You can see this must be some sort of transport. Now, if we add to the right-hand side of Vlasov's equation back in a term to account for collisions, we'll write that as the equation on the bottom of the page. This is called the so-called Boltzmann transport equation. You can see now it's a single transport equation for the distribution F. The right-hand side, which can be very complicated, can account for these types of collisions. I talk about this equation and its derivation in depth in my graduate course on the Navier-Stokes equations. Now, in binary collisions, the right-hand side might be written different ways. This is probably the most simple one, where there's some net rate in which particles are entering the so-called phase space in and out of each element. These are the so-called rates at which particles are scattered in and out of the volume, or the so-called phase space. We can also write this using this form here and simplify the terms. Now, if we take the previously derived Boltzmann equation with the right-hand side collision model, and we take the moments of the Boltzmann equation, we will actually recover the Navier-Stokes equations, which we've shown in this class. You derive the Navier-Stokes equations from the continuum theory of mechanics. You can also use this so-called quantum mechanics theory of Boltzmann equation to actually find and recover the exact form of the Navier-Stokes equations without any assumptions except those of the collision operator on the right-hand side from Vlasov's equation. That is fascinating because it has connected and put on a firm theoretical foundation the Navier-Stokes equations and their connection to quantum mechanics. That's wonderful, especially because of the fact that so many people dismiss continuum mechanics with the advent, of course, of quantum mechanics. Here I'm showing, and you're welcome to look through it on your own, the example of taking a particular moment and making some particular statements to find this form of the equation from moments. And of course, if you let Q in this particular form, which is a conserved variable, and set it to m the mass, you will have taken and reduced it to this equation here. Do you recognize that? That is exactly the vector form of the continuity equation of the Navier-Stokes equations with compressibility. That's partial rho partial t plus nabla, inner product of rho u is 0. Now, in this class, we're not going to work with the Boltzmann equations anymore, but I wanted you to see and understand the very big picture from a very, very high level so that when you hear someone is using a Boltzmann equation solver, which is very rare in itself and often for very specific applications, that you'll kind of know what they're talking about and you'll know the very basics of how to start understanding it and get involved in the research. You might be asking yourself, hey, who is Ludwig Boltzmann? Well, it so happens that Ludwig Boltzmann is pictured here on the picture on the right, from the late 1800s, and he was a professor. He was extremely intelligent. He lived from 1844 to 1906. Thankfully, he didn't have to see the First World War. He's very fortunate that way. He's an Australian, and he's probably has one of the greatest achievements ever of really defining and creating our concept of entropy, which is confusing to so many students. Earlier, I was talking about inequalities and simplifications of entropy. On Boltzmann's grave is actually an equation, and it's his entropy equation. It's not the Boltzmann equation, which we just showed at all. It actually states that S equals K of the natural log of W. In his time, many people wrote log for natural log, not ln like we do in America today. W is the number of possible states of the system. Simply put, this is a bit of a lazy definition. It's much more complicated. K is the Boltzmann constant. It's a universal constant, named after himself. In the entropy equation, S is the actual definition of entropy. Look how different this is relative to the forms of entropy which we reduced and shown in our class. He was a fascinating person. I encourage you to read about his history online. Let's make some closing comments about this course. I want you to take away these very important points. First, we typically evaluate the integral or differential forms of the equations of motion for laminar flow or turbulent flow or transitional flow. If we are directly evaluating these equations, which we showed in this particular class, we call these approaches in CFD direct numerical simulation because we are directly numerically integrating or evaluating the equations. They could be any set of equation. That would be the direct numerical approach. If you say direct numerical simulation, people will assume you are talking about You are solving the Navier-Stokes equations themselves in 3 dimensions, unsteady, and perhaps incompressible or compressible. On top of that, that is a very difficult field and is mostly in research, and we'll see why this is the case later in the class. Even for flows with very low turbulence, the direct numerical simulation or DNS approach is typically used. If you have any kind of meaningful Reynolds number, like 500,000 or 1 million, like we find in aerospace engineering, the so-called direct approach is usually not possible. Now, if it's a laminar approach, which is steady, we can certainly directly evaluate numerically the equations of motion with a solver, but that would not be necessarily called direct numerical simulation. DNS is a very specific term. Nonetheless, for laminar flows that are steady, we would typically simply solve the Navier-Stokes equations themselves without any modification. Now, I'm mentioning this because in practice, and most of the time, we do not solve these particular equations directly. We actually solve them with a whole nother set of equations which we create from these equations themselves that are turbulence models. And we'll be discussing turbulence models and their use later in the class. And there's many different kinds of turbulence models and fidelities, and they're created for all kinds of different flows and purpose. So not only do you have to understand the kinds of equations you're evaluating and their assumptions, and for the different flow regimes, you'll also have to pick the correct turbulence model for it if you choose that particular type of model and flow. It's very complicated, but I think at the end of this class, you'll see and get some insight into which models to choose for different kinds of flows, and you'll be practicing that as you use your solver, and we'll guide each other through that process. You can only learn this through experience. Nobody's going to be able to write a book or give a class which describes all this to you, and you'll have to, be able to understand it. That would be very difficult. Remember, there are alternative models for the fluids, but the Navier-Stokes equations today, from the time they were invented so many years ago, are the so-called workhorse equations. They are the equations behind all the simplified equations. And all the equations of motion that we'll be evaluating in this class go back to the set of equations. This is why their fundamental understanding is so important, and why I encourage you to take graduate classes in mathematics, physics, and engineering, focus on partial differential equations and the Navier-Stokes equations if possible, if you really want to understand the inner mechanics and physics of fluids. Otherwise, it's hopeless if you don't understand the mathematics. That's critical. Now, what we haven't done is address specific ideas for boundary conditions. We need to develop the boundary conditions because where we truncate the flow or where the fluid meets a boundary, we need to alter the solution or say something about it to find the appropriate physical solution. Remember, there are specific forms of differential equations that we might solve in certain situations. We'll discuss some of these in our next class. So next time, we'll talk about specialized forms of the governing equations. These are typically the Navier-Stokes equations with particular reductions. In your previous classes, you have done things in the opposite approach. You might have derived the Euler equations or potential incompressible two-dimensional potential equations first. That is not really the mathematically rigorous way to do it. You would want to find the Navier-Stokes equations and make simplifying assumptions to find these internal models. For example, the Euler equation. Even in mathematical research, Euler equations came first and then the Navier-Stokes equations. But it is shown today that the Navier-Stokes equations can be developed rigorously and then reduced to the Euler equations. They will also talk about the transonic equations, which are equations with specific reductions to resolve transonic flows. Reductions of those might be called the Prandtl-Glauert equations, which are named after Prandtl and student Glauert. I mentioned these two people earlier in the class when we were talking about natural flow visualization. If you remember, we might be able to use these equations to examine specific forms of the transonic flow. Another important set of equations is the boundary layer equations. These might be incompressible or compressible. We're going to look at the incompressible boundary layer equations. These are specific equations reduced from the Navier-Stokes equations to resolve a boundary layer. We'll also talk about the so-called parabolized Navier-Stokes equations, and to put icing on the cake, we'll talk about more. So we'll have a lot of fun next time talking about these reduced equations and where they should be used in CFD. It'll be a great time. Thank you very much for your time today. I'm your professor, Steve Miller.